Can start recording. Welcome, everyone. Now I'm happy to share with you. We have our second INNS webinar, and many more are to come. We're really much looking forward. Today, Ryan Samson will speak about AI for finance. And before I introduce into the topic, just some small, quick remarks. We are part of the International Neural Network Society, so these webinars are actually organized by the society, and everyone can become a member of it. There is a barcode here on the very far side where you can register. But even more interesting, just in a few days, I think it's still a month to go, there is a deadline for the paper submission for the International Joint Conference on Neural Networks in Rome. And I would be very happy to see many of you also live in Rome. I actually know that some of you who are here will come to Rome, but it's always great to meet some new people and re-meet old friends again. But let's go to the topic of today. And it's a very interesting topic for me because maybe we all heard that story, and I spoke to one of the greatest minds in neural networks, and he said to me, you know, Marcus, I had a PhD student, and the PhD student worked on deep learning neural networks to forecast maybe the values on a stock exchange. So can we do that with neural networks? And then I asked, yeah, what happened? The student never finished. The student was so good that he decided to just drop out of research
also
and
very interesting
use his algorithms to become successful in finance and did not finally finish the PhD. But the truth is, deep learning not always really works. And we have now with us a practitioner who will tell us that there are some other methods which might work better in several cases. So it's really good to have someone who actually works in a company. That someone is Ryan Samson, and he is the director of research in Qognitive. And that company, he will tell us much more about it, but that focuses on problems like what I have just motivated and tells us what really works and what not. Small spoiler, it's not always deep learning which will work. He actually published an article recently on RiskNet where he was showing some quantum cognition machine learning, which will work really well. And he promised me that he will speak a little bit about what he published in that article. So without further ado, I'm very much looking forward now to the presentation of Ryan Samson speaking about AI for finance. Ryan, the floor is yours.
All right. Marcus, thank you very much for the introduction. I'll make one small correction. I am a director working in research at Qognitive, not the director of research. We have a lot of brilliant people there and doing a lot of interesting work. I will talk about it a little bit, though it's not the focus today. If you give me just one moment, I'm going to share my slides, if I can. Okay, everyone can see this okay, I hope.
We do see the screen with the slides view mode on the side. I'm not sure if that's what you want to share. Now it's a full screen. Perfect.
Okay, thank you. Now, I'm going to start off just teasing Marcus a little bit, because when we were first corresponding about this talk, I came to the conclusion that I didn't have too much interesting to say, because we've, as he alluded to, mostly found good results with simpler architectures. And he said, well, that is interesting. So I'm going to show some of that and at the very least explain to you the mindset of a practitioner. A lot of the research that I'm going to talk about today was initially done at Duality Group, which was a quantitative hedge fund focused on machine learning techniques. Now I'm at Qognitive. Qognitive, we are focusing on a novel machine learning algorithm that we have developed, which we call QCML, that was referred to in the paper. Different approach than traditional neural networks, but can be applied to a lot of the same problems, and we face a lot of similar challenges. So in my article, I contrast the two. But let's jump in, and first I'm going to talk about what I'm not going to be talking about. So I'm not going to talk about any application outside of trying to forecast daily stock returns. So what are some obvious things that I'm not talking about? One is any type of reinforcement learning, adversarial networks, applications where you're trying to directly learn a trading strategy rather than a forecast of returns that would later become part of a portfolio optimization. Now, I'm not personally really familiar with this area, and maybe there's more work in this area that I don't know about. There is one paper, which I would encourage people to have a look at if you're curious, by Gordon Ritter. It's called Machine Learning for Trading. Gordon Ritter, he is also a practitioner and an academic, so he teaches at Master's in Math Finance program at NYU. I took one of his classes. I think he's a great professor, really nice guy. He does very good work. This particular paper, though, it's not done with real market data. It's done with simulated data. And I don't know why that is. It could be that he tried it with real data and it did not work. Or maybe this is the secret to how he makes his money and he didn't want to show the results that look too good. I don't know, but maybe for some of you here, this could be something to dig into, and you could try it with real data and maybe create a lot of buzz. I'm not going to be talking too much about LLMs. So the first way LLMs can be applied is there's a lot of sort of obvious to me, but there are lots of published papers going back many years about ways you can process text for feature generation. Now, before LLMs, this was generally done with what we would call bag of words approach, or maybe n-grams, where you're looking at small groups of words and creating, some simple vector representation from that, and proceeding to analyze that however you want, for whatever purpose, like sentiment or text similarity. Now, of course, with LLMs, you can get embeddings and potentially do a much better job capturing the content or ideas of a piece of text and how that's changed, which is pretty difficult with bag of words. The simple example is that you can add negatives like no or not to a sentence or to a paragraph, and that can be a very minimal change in terms of bag of words, but a very big change in terms of the meaning of the text. So LLMs are much better suited to capture that type of thing. I have seen a few papers starting to come out about LLMs for time series. Some of those, like let's say the ones I'm most skeptical of, but still very interesting, they'll simply take LLMs trained on text, then find some time series and find a way to just turn it into text tokens, feed that into the LLM, and apparently prediction works reasonably well. I haven't seen applications like, any time series application like that that's done within financial time series. It's done in low noise time series. I also have seen a couple of papers where they do something a bit more complex, where they're trying to embed together some type of text processing architecture along with the time series processing architecture, so that you'll be capturing some sort of information about the sentiment and directly feeding that in with another network that has information about the price series. That while I haven't evaluated any of those papers or tried it, I do think it would work. Would it work better than simple methods? I don't know. And people for a while have done simple methods of interacting informative past time series with return or price time series. Also, I'm not going to be talking about intraday forecasting because that It's not my experience area, and it's not what we did at Duality. We were focused on daily forecasting of stock returns. I have lost. Okay, thank you, Marcus, for helping me resolve the technical issues. So, as I was saying, I'm not going to be talking about intraday forecasting because that's not my area of expertise. A reason intraday forecasting could be interesting is because there's a higher ratio of signal to noise. And in general, with daily forecasting, we have a very low ratio of signal to noise, which is a likely reason why the simple architectures often work better. So I'm going to talk a little bit about a particular academic paper, which can motivate discussion and how, as I said, I think as a practitioner about evaluating results, how I look through a paper. So I'm going to pick on this paper a little bit, but I want to be clear. I think it's a very good paper, above average, and there's a lot of transparency, which I love, and that's not always the case. So this is called the Momentum Transformer, an intelligent and interpretable architecture. I don't know any of these authors, but as Marcus alluded in the intro, people who publish papers in machine learning and finance tend to end up in industry, and it looks like most of them are now in industry. I'm not surprised because, as I said, I do think it is a good paper. So in the abstract, they say that they're introducing the momentum transformer, and they say that it outperforms benchmark time series strategies, or sorry, time series momentum and mean reversion trading strategies. So this right away got my attention because when you're evaluating financial time series, the two biggest, most obvious effects that everybody knows about are momentum, which is returns typically over around a year time horizon tend to continue. But in a lot of markets, not every market, but in a lot of markets, shorter term returns on the horizon of like a month tend to reverse quite strongly. So one way I've seen a number of papers make results look better is by essentially ignoring that mean reversion exists when they're setting up their benchmark. And then you create some interesting method for learning momentum and you learn something stronger, but it may just be picking up on mean reversion. So starting to read through the paper and understand how they set things up. The first quote I have here, the univariate TS mom, they use capital TS mom for time series momentum. So the TS mom strategies we focus on differ from cross-sectional strategies. So this is good to know when you think about the results. They're not looking at a cross-section of assets where you're going to be long one thing and hedged by being short another. Here you are long or short individual assets. Well, in this paper, I believe they went long or flat, at least for the benchmark. That's fine for CTAs. That is fine for some hedge funds. They'll allow some risk, but usually not a large amount of risk, taking directional time series bets, especially in futures. This paper is looking at futures trading because, of course, if you're trying to time the market while you're long or short the market, you are not hedged. It's a lot of risk. So when I look at a paper, my level of interest is often dictated by how well they controlled for risk. And this isn't a type of strategy I would necessarily have employed in the past, but it's not invalid. And it's very clear that that's what they're doing, so that's fine. They also mentioned that their target is 1 day forward Sharpe ratio. So the back test portfolios they're creating here, they rebalance every day. Rebalancing every day, I actually like that, prefer that. That's realistic. That's what practitioners do. Forecasting 1 day forward, it's fine, but as when I just talk about our cognitive paper, you'll see we use a longer horizon, and typically you'll get better results in daily context when you try to predict a longer horizon. Just another quote there about how they're maximizing Sharpe ratio. I thought that was great because most papers, they'll just do mean square error. In fact, my paper, that's what I did. But in realistic applications, we often did something that was risk adjusted. So I thought that was a nice touch here. So this is the main result. I really subset the table. The table was much larger. They had more columns. They broke down the results into different time periods. In particular, they looked at the markets during the COVID crisis, and they talk about how some of their architectures are better at responding to the new environment during the crisis. So that was really interesting. I love to see a breakdown over different time periods. I also threw in one of their charts. I love to see time series charts because academic papers don't often include that. But as practitioners, we look at time series all the time. We want to see, besides just a strong Sharpe ratio, we would like to see consistency and performance over different subperiods, rather than something that you have a short period of time that's very strong and other periods of time that are flat. We don't like that in strategies we deploy because, of course, we're accountable to investors. Well, in hedge funds, oftentimes they're getting performance numbers every day or every week. Now, looking a little more closely at this table, the first row is the results of going long only all of the markets that they're trading here. It's a mix of equities, commodities, fixed income, liquid futures. Then they have a row called TS MOM. But the main question I'm asking on the slide is, what is TS MOM? Then below that, they have all of the more interesting machine learning architectures that they tested. And we're going to focus on Sharpe for a second. We see, okay, if you're just long all these contracts all the time, Sharpe is around 0.5. If you use traditional momentum strategy, it's Sharpe around 1. And then these various architectures, the results range from around the same as the time series momentum to much better. But like I said, we want to know, well, what is TSMO? So I start digging through the paper, and actually it's not defined in this paper. While I was trying to find it, reading the appendix, rereading the text, I did notice some interesting notes that I want to bring attention to that I didn't notice the first time. So the first comment, they say that they Windsorrize our data by limiting it to be within 5 times exponentially weighted moving standard deviation relative to the average using a 252-day half-life. Windsorization for feature generation is very, very common for practitioners. You don't want inputs to your model that are driven by extreme observations, because that will cause you to take extreme positions, which that can be very risky, of course. But here, they're not clear if they're doing this to just the features that they generate or to all of their return data. And it sounds like they did it to all of their return data, which would be a little bit strange to me because it's not really realistic, and it's not something that we do to trim the target when you're evaluating returns. If you want to trim the target for training your machine learning model, that's actually very reasonable as well, and something that I have done. But I would like a little more clarity around this, and it just makes me scratch my head about what they're doing. The second quote here, they said they hold out 10% of the training data, and they call that validation data. And as they do their hyperparameter optimization, they're looking at the results in that validation data. I love this. I love that they knew to do this. I love that they were transparent about this. This is something that a lot of people don't do. They'll validate, or sorry, they'll tune hyperparameters by looking at their test data set. So this is good because it should lead to less overfitting. Okay, so another great thing about this paper is they posted their code online. So this is becoming more common, but traditionally it's not something you see in financial economics papers. Here they posted a lot of code, and I have to say, I thought their code was beautiful, really nice. PEP8, I actually cut a lot out of this function before pasting it in. They had a beautiful doc string, but this is a one-line function, and I didn't want to clutter the slides, so I simplified things here. So what is time series momentum? Well, we look in their test script, they're calling a function called intermediate momentum position, passing some argument as 0, and then passing the returns data. Looking at what that function is, W is a weight, which is combining or it's tuning the weight that you would put on the sign of the monthly return and the sign of the annual return. So I'm sorry, I misspoke earlier. I said they were going flat or long, but here they're going long or short, the asset, based on the sign of the return. They chose W as 0, so surprise to me to get into this, because in their abstract, they said they were going to look at mean reversion and momentum. But in the paper, ultimately, they only used momentum for their benchmark strategy. And further, they're just using the sign. So they're throwing out a lot of potential information in the magnitude of the return, just purely binary, long or short, based on the sign. So this time series momentum is really, really simplistic, really naive. And keeping that in mind, let's go back to that main result. And I didn't mention this earlier, but it's good to know, well, okay, what sort of features are they using? And they're doing something very reasonable. They're looking at returns at different time scales, monthly, quarterly, biannual, annual returns. The returns are normalized with volatility. That was a good touch, which practitioners definitely do that within the macro space, especially. And they have some moving average, convergence, divergence indicators. So there's a big set of features, all continual valued, a bunch of different time horizons. They're feeding those into these complex architectures. And if we look, we see there's a couple of them, the decoder only transformer, the conv transformer. Those complex architectures are barely doing better than this naive momentum only that destroyed all of the information in the return variable to only use the sign. So all of a sudden, this looks a lot less impressive, which is not to say this is not impressive. It's not to say these other architectures are not interesting. As you can see, they're producing some very strong Sharpe ratios for some of them. But the benchmark here is not particularly credible to me. So now, looking at their main result, we say, okay, I don't really know how to contextualize this result. So now I'm going to move on to the cognitive paper, Quantum Cognition Machine Learning, we call QCML. As I mentioned, this is a novel machine learning algorithm that Cognitive's chief scientific officer, Corinne Muselian, came up with this idea, and we founded a company to further this IP. This particular paper focuses on applying this technology to financial forecasting, and that's why I'm going to talk about it here. I'm not going to go into the details of QCML today. If you're interested, if you just search the title of the paper and the author's names, you should be able to find it. or if you find Cognitive's website, we do have it posted on our website. And if you have questions, feel free to reach out to me. I'm always happy to talk about this. And since this is my opportunity to plug Qognitive, I'll take the opportunity to mention that we are doing what I think is very interesting work. As I mentioned, this technology can be applied to a wide range of problems. We are working on financial applications with a couple of different asset managers and banks, but we are also looking at things like medical testing, drug discovery. We're hoping to do some work on text processing. So really a lot of things that could be applied to. And I will say we are looking to hire. We're looking for talented machine learning engineers, developers. Everybody wants to be in machine learning right now, but it's hard to find good talent. We need people who have looked at hard problems and complex architectures and thought about why those architectures are set up how they are and how to modify them. We actually have ways to integrate our technology with neural networks. So we're looking at hybrid architectures. We also need people who can dig into, the guts of things, like if we're implementing in PyTorch, how is it backpropagating gradients? Is everything working correctly? How can we make it more efficient? So if you have the stomach for being at a tech startup, we have had great traction in funding. We've got, I think, like 16 people now. We need more talented people, and feel free to reach out. As I said, we are looking for people. Now, the paper, as I said, we're focused in this paper on showing off our technology, but we also compare it with a neural network architecture. And the point is to show that we do, because this is some novel forecasting technique that nobody's ever heard of, and show that we can pick up on similar things to a neural network. In this paper, we're not saying that we're massively better than a neural network, but it's interesting to go through some of the setup of this paper so you can see how, with our experience running a quant fund, we thought about setting up some of the details of the forecasting problem. So first, what is our return test? Our return test is a cross-sectional test. And we're looking at individual stocks here. There's a universe of around 1,500 stocks, daily returns, and we're forming what's called a Markowitz optimal portfolio. So if we have some covariance V and we have some forecast F, then if you do a simple mean variance optimization, which is what you would do if you were, let's stay with, but it's a reasonable thing to do, and it's how many people actually optimize their portfolios, as a mean variance optimization with constraints. If you have no constraints, the simple solution is V inverse times F. In this case, I say that our forecasts are projected away from input and control features. So we are forming an optimal portfolio W, which is V inverse F. That portfolio W has no exposure to input and control features, which means if you take the dot product of that vector W with the vector containing the values for an input and control feature, the result is 0. How do we do that? What do I mean by a projection? This is in one of the footnotes in the paper. So going back again to this idea of mean variance optimization, if you're trying to minimize the expected return plus some penalty for covariance of the portfolio, and you add a simple linear constraint that you want no exposure to some set of forecasts M, you can solve that and put it in the form where W equals V inverse times some matrix R times the forecast F, where R has this form that you see in the middle of the footnote there. So we call R a projection operator that projects away from M. It was derived by looking at our investment process. How would we actually form a portfolio that maximizes expected return, subject to some penalty on risk, and subject to this constraint. And if you look closely at that equation for R, you can see it's actually the residual from an inverse variance weighted regression of F on that matrix M. So our projection operator is equivalent to this residualization from a regression. It's consistent with how we're actually willing to manage portfolios and take risk. And because we're residualizing to not only some set of controls, but also the inputs to the model, that means we're going to focus on learning just the nonlinear component of the inputs. And what is the target? So I mentioned in the paper we were just reviewing, they have a one-day forward target, and we typically see better results with longer horizons of daily when using daily returns. In this paper, we used 15-day forward returns. At Duality, we sometimes use 1 day, more often anywhere from 4 to 8 days. And I'm mentioning some of the things that we're controlling for: beta, size, industry dummies, and the target. We're also, after we project it away, we cross-sectionally normalize it each day. Now, why might I cross-sectionally normalize my target? Well, if you look at the paper, you look at the details of the input features, those are all cross-sectionally normalized as well. And if you imagine you're trying to learn some relationship between these inputs, which always have a standard deviation 1 distribution relative to returns, which would have, without normalization, would have a very widely variable amount of standard deviation, it may be difficult for the model to learn. So it's something to think about. What's the distribution of your inputs? What's the distribution of your target? If one is normalized, the other should be able to either also be normalized or have some information about that. So you don't necessarily have to normalize it. You could, for instance, add some context variable as input, like what's the volatility of the market right now. Additional detail is on partitioning. So in this paper, we decided to break up our universe of 1,500 stocks into small groups of around 50 stocks, and we would learn a submodel on each one of those individual subgroups. Of course, that's going to be very noisy because it's random which stocks are going to be in each of those subgroups. So we need a lot of different partitions. And in this case, we did 100 different partitions. And that way, each individual stock is in 100 different submodels with other stocks. And you'll start to get some more robustness on each of those models. If you were using larger groups, you wouldn't need nearly that many partitions, but using multiple seeds, using partitions is very important. So taking a break for a second to refer to some duality tests, looking at the importance of multiple seeds. We had some work that one of my colleagues did where we had 13 neural net configurations that Duality Group was actually using in production. This particular set only differed by input features. They were trained on the full universe of 1,500 stocks, and they were using 16 partitions for each model. So we thought, okay, we're training on the full universe. So each partition is going to have its own random seed derived from the main seed. The subpartitions are going to differ only because of that random seed, which means the initialization point of the neural network will differ, and the order in which the training data is used will differ because it's being scrambled when it's applied. We're using stochastic gradient descent. The final forecast is just averaged across those 16 seeds. So we were doing some other tests where we started to wonder if we were using enough seeds or enough partitions. So we ran these 16 partitions with 4 different master seeds. Then we looked at the pairwise cross-sectional correlation of forecasts across each seed, and then averaged across those 3 pairs by model. And that's the values you see on the right. There are some that are as low as 0.58. So even with 16 partitions, where the only difference in how these are trained is the initialization point and the order of the training data, there was still quite a bit of difference. So this is something that's really important that some people are not aware of. When you're training neural networks, especially with noisy data, you need to use multiple seeds. And it's worth mentioning that the prior paper we were reviewing, there was no reference to seeds in the paper. I didn't have a chance to dig through their code. Like I said, that's one of the things I love about the paper. It's very transparent. Their code's beautiful. If anyone's interested, you could go and dig and see if they did that with their neural networks. If they didn't, then that's another reason to be a bit suspicious of the results. Some few additional more details about the neural network setup that we use in this paper. So I have this quote here where I said we followed the approach of this reference 14. Reference 14 was this paper by Gu, Kelly, and Xu, Empirical Asset Pricing via Machine Learning. This paper is pretty well known within quant finance because of the author's affiliations with AQR. And it was a strong result. It was one of the early papers showing a practical application of a neural network. So essentially, to avoid debate, I followed their architecture. There's 3 hidden layers, 32, 16, and 8 nodes, batch normalization, ReLU activation, mean square error loss, using Atom Optimizer. So now you get the confession from the author of this paper. One of the things I spent the most amount of time on in this paper was trying different neural network architectures because I wanted the first neural network test that I did, which the only inputs are value and momentum. I wanted that to look better because it doesn't look particularly good. And I was worried that people reading the paper would think, oh, they chose some example where neural networks look terrible. That was not the intent at all. I wanted a simple value momentum input because that allowed us in the paper to do surface plots of the forecast relative to each of the 2 input features. And there's prior work looking at interactions of value momentum. So you can see that the neural network confirms some prior work on the interaction of value momentum, and our QCML architecture also confirms that prior work. It captures a very similar surface to what the neural network is capturing. In my opinion, it captures it a little bit more cleanly than the neural network even, which you can see. I should have put the surfaces here, I'm sorry, but again, you can look up the paper. Now the truth, all these different architectures I tested for the neural network all made very, very little difference. So this particular one, which was closest to the reference paper, was a little bit better. I went with it again because I like that it's close to that well-known paper. So it avoids an angle that people can criticize our paper. But if you did this with 1 hidden layer, it would not look that different. This is one of our main results from the paper. So as I said, I do a couple of different models, first with just value and momentum as inputs to show these surfaces, to show the neural network is reasonable and QCML is reasonable. But then for a more interesting application, we take several signals, which are just commonly used, well-known features in quant that are predictive of returns in some linear capacity. I set up these other learners, neural network and QCML, to learn only the portion of returns that cannot be explained linearly. So that's a higher bar than most other papers will use. But I really, as a practitioner, don't care so much about learning the linear effect, because that's a big portion of the effect that I don't need a neural network for. I want to use the neural network to capture the interesting part of the distribution that I can't capture linearly or predefine in some other simple linear transformation that I might think of. But so we show a basket of these linear strategies pooled together. They produce a Sharp around 1.17. Then you add the neural network in, you get up to around 1.38. Instead of the neural network, you add QCML, you get 1.43. You add all of them together, you get 1.56. So that's what we're trying to get people interested in. Of course, this is partially a marketing paper, because at Qognitive, we are trying to get people to utilize our new technology. We have an API people can use. But on the right, we're showing how you might start with some linear strategy. That's the blue line. The orange and green are adding in these non-linear effects from respectively a neural network and QCML, and red if you add both. So like I said at the outset, here we weren't trying to say that we're strictly superior to neural networks, but it's a new machine learning approach. It's reasonable, it's additive, and can actually have a strong impact on a realistic trading strategy. So the main purpose of going through all this, I was hoping to show you, with my background as a practitioner, this is how I set up the problem to appeal to a practitioner, to show the proper controls and the proper additive value of what you're forecasting here. But I promised to talk about not just how I set things up, but what architectures have we tried over time? What was interesting? What worked well? What didn't? So I'm going to go through some of that now by referring back to a range of tested duality. I'm going to start with something simple we did when we were revisiting. As I said, we had a number of models in production. I referred to 13 that were in one architecture. We had a number in some different architecture. In this test, we said, okay, we have all these neural networks. They have one hidden layer with 10 nodes, and we weren't using dropout. Is that the right choice? Let's revisit this and try a bunch of different simple, fully connected layers of different sizes, multiple layers, different dropouts. And you can see nothing was really better here. Dropout wasn't obviously helpful. Increasing or decreasing parameters was not obviously helpful. Multiple layers was mostly worse. There was one that happens to be about the same, but really nothing to get excited about here. Well, we had the idea, okay, this is our production set. These are models that we developed, having already chosen the architecture. So maybe this is biased. Maybe these models work well for this architecture because we developed them on this architecture. So let's try random feature sets. So we did 78 neural network looking at random feature pairs. And you see these Sharp ratios are not good. So just throwing in random feature pairs and averaging across all those pairs, not a great way to design a process. But you see, again, there's really no obvious benefit from these different sizes. Dropout is not helpful. We also did this for multiple layers, but I excluded it because it's more of the same. Now I'm going to refer to some research where I could only pull the results from old presentations, so it's going to be hard to see some of this. I apologize, but I'll do my best to summarize the key points. This is work that we did as a prelude to test complex architectures. So again, as I was explaining going over our paper, it's important to us to make sure the benchmark is well defined. So here, we wanted to well define how we would do a simple, fully connected architecture using time series of inputs. So we're looking at 44 interesting features here. A simple 10 node hidden layer. In this mean results, mid left of the slide, we see lags either 1 or 8. With 8 lags, then we start to look at different amounts of dropout. Okay, so we see adding the feature lags here was clearly very helpful. Adding dropout, no meaningful difference. Below the mean results, we have the aggregate results. So we just took the simple 8 lags, no dropout, and we averaged the forecast across all of the inputs and then looked at the Sharp of that. And that aggregated up very nicely. So the mean of around 0.5 for 40 signals, but there's very low correlation. You aggregate that up into a single forecast and you get a pretty nice Sharp ratio. You can see the test set was close to 2 here. Now, moving from the individual features, we looked at feature pairs. We noticed an interesting pattern here where some features were clearly strong features where whenever that feature is in the architecture, the results are better. So we decided to break things into strong and weak pairs. And in the bottom of the page, you see again an aggregation result. The first row is if we aggregated all pairs. That's actually a little bit worse than if you just aggregated all of the forecasts from individual features put into the model. But then if you filter for strong features interacted with weak features, then it looks a little bit better. From there, we did a lot more work on features, which I'll skip over because it's not particularly interesting, but the idea was focus on these strong features as the key drivers of a model, add in the weak features as interactors, and we end up with a bunch of interactors. And indeed, we saw as we're adding in those interactors, the submodels don't massively change, but generally they slowly improve with these features that can add some interesting context. And this was the final model. On the left was the research period. On the right was the out of sample period. The way we ran research is as a researcher was developing a model, they would do all of this, hyperparameter search, feature selection, limited to data prior to a certain time period. They would present the data once as a group we were satisfied with the research and signed off on the research, then they could do what we called opening the embargo, which is looking at the most recent few years. So that chart on the bottom right is embargo. That crazy blip on the left is the COVID crisis. We do see a lot of shorter frequency strategies show that pattern during COVID. When you're looking at these naive returns, these Markowitz type portfolios, once you go into a backtest, a constrained backtest where you're adding a lot more constraints like position limits, it controls risk much better and you don't see that. So we weren't particularly worried about that. Here we see that a lot. The embargo Sharp was 0.7, which is not bad. Certainly could be additive within a larger process, and we added this into our process indeed. But this was the jumping off point for more complex architectures, like I said. We looked at some convolutional neural networks. I didn't have a chance to dig up those results. They were embedded in Slack messages. They weren't interesting enough even to present. But I'm going to show some RNN results. Here we expanded the feature set from, I mentioned 40, around 40 with the fully connected layer. Here it's closer to 70. There's obviously no hope of seeing these numbers, but they're mostly positive because we're limiting ourselves to input features that we already know are interesting. Average Sharp around 0.44 for the simple fully connected layer. Then we looked at a simple RNN, 5 nodes using only the final output, and the Sharp is 0.47. It's better. It's not hugely impressive. From there was a lot more experimentation with different ways of combining RNNs, multiple layers, different ways of doing this, the sliding. Do we want to use each of the hidden states over time or only the final state? The one that we ended up using was one of the simplest ones that we tested. And really it's just a very simple RNN and a residual connection. And how did it look? Tuned in sample. The fully connected simple one-layer architecture was a 1.33 Sharp, and this was a 1.64 Sharp. So it's a 20% improvement, which it's not bad. It's an improvement with a more interesting architecture, but there was a lot of fine tuning here, and this is an in-sample improvement. So you have to take this with a grain of salt, and you can see why I'd say, okay, we're not super impressed with this more complex architecture. This was the final result. I didn't put the out of sample Sharp here, so the chart on the left is the research time series, the naive returns. I put a vertical bar to delineate the embargo period. So the embargo Sharp here was around 1.7. That's a very nice performance during an embargo period. You'd think, okay, this is exciting. This is a new architecture, some really diversified model combining a large set of features and interactors to create, something like 100 submodels aggregated together. We were excited to add into the backtest. We thought this is going to be cool. This is going to add a lot of value. I haven't been showing many backtest charts, but on the right here, I have the relative returns of the backtest. So this was the returns to our production backtest after adding this new cool architecture relative to before adding it. And you can see it improved, but it wasn't particularly impressive. It added like a couple percent to a backtest that was generating like 180% returns. So really marginal. And if you focus on that embargo period where the naive returns were Sharp close to 2, the impact on the backtest is flat. So we were disappointed to see with all this engineering, we weren't capturing anything, or we were not capturing much different than what we were already capturing with our other simpler neural networks and other non-neural network forecasts. And the sad bullet at the bottom, this was later dropped and replaced with an even simpler architecture that I'm not going to go through the details of the architecture because it was the idea of one of my researchers, and he's moved on to another quant shop where he's probably using it. But it's something that has even fewer parameters than a fully connected architecture. So in the end, the simplest thing won. So final comments now. As I said, there are some other things that we experimented with, like convolutional neural networks, LSTM, attention. None of those had made the cut to make it into the process. I don't think it would be interesting to go through more of, and here's something else that didn't work, here's something else that didn't work. But I hope you get an idea of how we think about setting up the benchmark. Now, of course, Duality was a small company. We were a small team. we didn't try everything. We didn't try everything perfectly. And going back to this paper that I discussed at the beginning of the talk, looking at their results across these different architectures, all these different types of attention, there's a big variation in results. So just saying you tried a type of attention, not necessarily enough. The details matter. But since I haven't tried to replicate this paper, they don't mention seeds. I don't know how noisy their results are. And we always need to be a little bit skeptical because the incentives for publication are very different than the incentives of somebody who's trying to actually use in the real world a forecasting model. For publishing, of course, we want our results to look as good as possible. So maybe we don't use as many seeds as we should, or maybe we use a benchmark where we turn the signal into a simple binary signal using only one signal, ignoring other known effects. As a practitioner, we care about getting the best possible model, which means we're always going to be thorough in what we do. And a lot of times the right answer is to reject something that's new or complicated. So something to keep in mind for those of you who are interested in working on actual practical finance. It's a different way of, different mindset, a different approach. If you're in academia, well, I guess your takeaway could be, oh, here's a nice way to make my results look better. I hope instead your takeaway is, here's a mindset I can use when I'm reviewing my colleagues' papers to be a little bit skeptical of how they've set things up. And so, you know, that's my final takeaway. Whatever architecture you're looking at, make sure you set the benchmark correctly. Make sure that you're evaluating something that is realistic and really suited to the problem that you're tackling. I think this is pretty common practice in the broader machine learning community where people publish their best models and results and even upload their weights and training data. But within finance, which is traditionally a very secretive community, it's much easier for people to get away with this type of thing because who's to define what's the best momentum benchmark? That's a lot of investors think of that as their secret and they don't publish it. So when you're publishing a paper, you can say, oh, well, I need to do something that's reasonable, not necessarily what's best. With that, I will end things. Thank you all for your time.
Thank you so much, Ryan. I see some other people were also very happy, as I see in the chat, and whoever has a question, just raise your hand in Zoom or type it in the chat if you don't want to be visible. And at any time, you can also the others now show your video again. We are at the moment still recording. Later, I will close, but let's have some questions. And is there already a question? Yes, there is. So please, go ahead, Pilar.
Thank you. Yeah, I appreciate very much this talking, especially the fact that there is a important issue here that deep learning is not everything, and I think the community of neural networks we require to be clear to everybody this fact. It really worries me that sometimes people don't talk about neural networks, but they use deep learning as a synonym word. Then I would like to know if there is the advice about how can we broadcast this idea that deep learning is not everything.
You know, it's a good question. And definitely there's a lot of hype in the industry right now. I would say, at Qognitive, most of us are pretty firmly in the camp of skepticism about a lot of claims that are happening right now. Particularly with LLMs, we're definitely seeing some incredible work. At the same time, I'm deeply skeptical that if we just continue scaling these things up, you'll get emergent consciousness or true intelligence. A lot of these things go in cycles, and ultimately, maybe I'm wrong. The truth is, there's a lot of fundamental properties of intelligence we don't understand at all. And a lot of, there's been so much money going into machine learning in the past few years, so much more interest, so much growth in capabilities that there's a lot of misunderstanding about what it can do in any context. I think all we can really do is do our best to be vocal about being honest about what the capabilities are, because unfortunately there is a lot of disinformation. There's a lot of people trying to profit off of overselling what's possible. I think naturally over time, the general public will understand the limitations, but it just takes time for people to see the truth. Hopefully that addresses what you were wondering.
Thank you. Yeah, that's fine. Thank you very much.
Yeah, I have a small thing to add there as well. You highlighted already, Ryan. Danilo, I give you the word in a moment. I just want to add, you highlighted in your presentation already, have multiple seeds, do multiple runs, but then also report the variance, maybe do statistical significance tests, all of these things. Even in major, highest ranked publication venues, conferences and so on, I'm missing that very often, that is happening. And it was a thing I learned very early in my PhD, and I think that's something we need to continue teaching. By the way, the one who taught that to me was not Joshua, but Sami Benjo, his brother. So very first presentation I gave as a very young PhD student, he said, "Did you do a significance test?" And from then I always do a significance test. So that's very important to do.
Yeah, that's a great comment. I really appreciate you bringing that up again. Because we see that even from practitioners now, as at Qognitive, I'm interacting with more practitioners of other companies. We had a test we were running where we saw they were using a random forest method. We were using our QCML method, and we were getting a much better result. And they were like, well, we don't see the random forest doing, like, we were getting a very different result from you. And it turned out, yes, they were running one seed in terms of how they split up the train test validation data. And there was massive variation across seeds. We were running like 50 seeds, and there's a big influence from a small number of outlier observations, depending on which cut of the data they were in. So yeah, great point, Marcus. Thank you.
Danilo, please.
So thank you very much, Ryan, for your expert insight and very, very honest overview of what's going on. I was also, I very much prefer interpretable models and models on the edge, small models. And I was really encouraged that your models you presented are all very small. It's 3, 4, 5 layer neural network, if at all, and so on. But can you maybe give a little bit of a further insight into the size of neural network you use, or could be used for financial analytics, and what are maybe the issues with interpretability of the results we can get with neural nets in financial modeling?
Sure. So in terms of size, I mean, it depends how patient you are for runtime and how much money you can spend on compute. So one thing you can do to to allow for more complex architectures is train more smaller models. So when I was going over the QCML paper, one thing, remember how we did partitions there? We trained on groups of 50 stocks, so really small submodels, and then we train more submodels. Gives you more diversity, but it also allows for heavy parallelization within some cloud computing environment. So Duality, we were using AWS, and we could spin up hundreds of computers at once and send a problem to each of those processors, aggregate it up. But the AWS bill gets very high very quickly. This is why Jeff Bezos is so wealthy. Okay, practically though, in terms of how complex can an architecture be, I mean, we were running things like you saw we did some tests with 100 nodes with one hidden layer. I think a couple of times we ran that with like 3 hidden layers. It's a pretty large parameter set. It's feasible if you're willing to wait several hours of runtime. Most of the things we would limit to like 10 hidden nodes, and we would like things that we could run in like a couple of hours. You mentioned simple models. So in terms of how did we want to get interpretability, there was a few things we could try. So one is you look for consistency in different data sets in some way. So that could be testing in different markets. Do the same features work well together? Or, for example, we had several different ways of capturing mean reversion, which were themselves interesting models. In some cases, like some custom Bayesian architecture designed to capture market dynamics in an intuitive way. So say we have like a half dozen mean reversion models. Now we want to enhance those mean reversion models so we can feed that into a neural network with features that we expect would be reasonable to interact with mean reversion, like let's say value momentum, for instance, might be reasonable. But because you have different mean reversion models, you can look at each of them individually, adding the interactors individually, and look for consistency and say, okay, I only want to add interactive features that work across all of the mean reversion models, because maybe I'm not sure why this whatever accounting ratio happens to condition well for mean reversion, but at least it's consistent across a bunch of different models. And then last, you can try to look for real economic interpretability in some cases, at least the low-dimensional cases. So like I said, in that QCML paper, we plotted the forecast relative to the value momentum inputs to create a surface plot. And we showed that the shapes are consistent, and they're consistent with prior work on value momentum interactions, which was actually even done on a different time period. So there you can get comfortable that you're learning some effect that makes sense. You can look at where momentum and value are weaker or stronger, and you can have some economic rationale for that. As a practitioner, though, I will say I've seen a lot of cases of people test things and then they come up with a story after the fact. So I think it's good to try to have intuition for why things should work, but keep in mind that there can be a sort of data mining there as well in terms of creating the story to fit the data.
Thank you very much.
Thank you for the question. Appreciate it.
Yeah, thank you very much. I think we are now done with the question answering part. We will, though, in a moment still have time if you have some questions which we will not record. Just want to mention we have already a next webinar planned, and this is in less than a week. It's actually this time not on Thursday, but already on Tuesday. where Professor Dutch will speak about the novelization of neural networks, the current and the future perspectives. And that's a really hot topic at the moment, right? Just 2 days ago, the Nobel Prize was given to a few AI researchers, among them Geoffrey Hinton, and the several different key players who played a role in Google DeepMind for finding or creating AlphaFold, which was really helpful in many application areas. So I think it will be quite interesting to listen to Władysław Dutch and discussing about who all contributed in all of these aspects, which finally led to Nobel Prizes for researchers on neural networks. Just want to also mention that I was there in some additional seminars and meetings Geoffrey Hinton had, and also he by himself mentioned already he feels sometimes a bit sad that he is like the only one standing there, because there were many other people who played a big role. And he mentioned also some people who unfortunately passed away already. He personally credited a lot also to Rummelhart. But we will see much more on the 17th of December, same time. So put already in your calendar, it's already out. You can register for this webinar. Be with us. There is also just a reminder, there are other activities the International Neural Network Society is organizing, not only these webinars, but mainly also the real conference where we can have real coffee breaks. And the next one, the next physical conference, will be in Rome, in Italy, in the end of June and beginning of July. I will be there. Many of us who are now here in the room will be also there. And I would love to have now a real coffee break with you. We don't have that, but this time we will really stay online. So while some of you now register to become part of INNS or will join the conference, everyone else also stay with us now. We will not close the room today. Just pause the recording or stop the recording and have a bit of a chit chat afterwards. Thanks again, Ryan, and thanks everyone for your questions.
You're welcome.